Take a look at this circuit. This is the bridge rectifier, as it is visually similar to the Wheatstone bridge. It does not require a center tap transformer, which is an advantage. If the step-down voltage is not required, the transformer can be eliminated altogether. However, 4 diodes are required, which isn't an issue since diodes are inexpensive. Let's see how it works. In the positive half cycle of Vs, D1, R and D2 conduct. This way, D3 and D4 are reverse biased. The two diodes mean that V0 will be lower than Vs by 2 diode drops. This is the only significant disadvantage. In negative half cycle, the polarity of Vs is reversed and D3 and D4 conduct through R. Notice that current still flows in same direction through R, and so the output is again unipolar and positive. See this graph. Let's try this on multisim. You can see that the exact same circuit is replicated here with 4 diodes, a resistor, an input voltage source, and also an oscilloscope for measuring the output voltage. Here at the terminal A, we have the output across the resistor R1, and at terminal B, we have the input voltage V1 for comparison. So let's play it. You can see here that this is just like the figure we had in our lecture. However, notice that the output and the input have a difference of 2Vd. That is why you can see that the difference over here is slightly larger than the one we had in the full wave rectifier. To calculate PIV, consider D3 during positive half cycle. The reverse voltage across it, cathode minus anode, is given by V0 minus Vd2, which is V0 plus Vd2. Their maximum values are given by Vs minus 2Vd plus Vd. This equals Vs minus Vd. This is about half the value for center tapped full wave rectifier. And that's another advantage because high PIV diodes are costlier.